All right, so now we're going to start talking about nuclear equations. I'm going to start talking about nuclear equations. Yes. Nuclear equations. Yes. Now, nuclear equations show what's happening when we have nuclear decay, we have nuclear fission, and we have nuclear fusion. Nuclear equations show what's going on with nuclear decay, nuclear fission, and nuclear fusion. So let's look at what fission is. And fission is the splitting of the nucleus of the atom. Splitting the nucleus of the atom. So what does that look like? Well, if we have a nucleus of an atom, or a large atom, nucleus of a large atom, and really large atoms are unwieldy, okay? They're not very solid. They're kind of squishy, and they kind of wiggle. And so if you take and stick just one extra neutron on there, so here's a neutron, okay? And this is a large atomic nucleus, the center of an atom that's really large. And you hit it with this neutron. You don't hit it like split it like a bullet split something. You put it on there and it just makes the thing even more unwieldy than it was before. Okay, so it's going to basically split in two. All right? And so as a result of it splitting in two, then we're going to get a couple of smaller nuclei. In addition to the smaller nuclei, because of the way that the number of neutrons in a nuclei needs to stay stable, we're also giving up some extra neutrons when that happens. And so those neutrons... Uh-oh, are you okay? Yeah. Those neutrons then can go on and hit another large nucleus and cause that to split up. And so the result of all of this is that you can have what's called a chain reaction. Okay? The original neutron causes one atom to split and breaks into larger nuclei. But then you get extra neutrons too, and those go on and hit some more nuclei, and those split, and they hit some more nuclei, and those split, and pretty soon you got this huge chain reaction going on. And so when you have an uncontrolled reaction like this, if it's uncontrolled, you have a nuclear explosion. And so you may have seen old black and white photos of the result of the bombs being dropped on Hiroshima and Nagasaki at the end of World War II. That was the result of this process. Those nuclear bombs had some what's called enriched, one bomb had enriched uranium in the center. Enriched just means that most uranium is 238 with a small, tiny small amount of 235, and what you do is you do some chemical and physical treatments of it to get rid of a lot of the 238 and have more 235 than typically you do. Then that 235 is put inside a container, and you pack TNT around it and explode all the TNT around it, and it causes a chain reaction that gives you a nuclear bomb. Okay? The other nuclear bomb they set off didn't have uranium in the center, it had plutonium in the center. But it's the same process. You pack TNT around it, set all the TNT off at the same time. The implosion then causes a chain reaction, a fission reaction that creates a nuclear bomb. Now, fission is kind of the opposite of fusion. Fusion is getting two nuclei to stick together. What? Oh, back there under the owl. Stick together into a larger nucleus. So we're going to take two smaller nuclei, and we're going to use a lot of heat and pressure stick together into a larger nucleus. So a lot of heat and pressure, like the kind of heat and pressure you have at the center of the sun. Yep, mutual heat and pressure. And as a result of that, then, we're going to get an atom, and we're still going to have some leftover stuff, usually a neutron, often, most of the time, not always. And there's a series of nuclear reactions that happen at the center of the sun. There's a series of nuclear reactions, fusion reactions that happen at the center of the sun. But the final one in the series that gives us all that helium that's created starts out with an isotope of hydrogen called tritium. Okay, so a mass of 3 and an atomic number of 1. That means I have 2 neutrons and 1 proton. And you're also putting that together, at least this is the theory, with a form of another isotope of hydrogen called deuterium. So this is a tritium and this is a deuterium, and they bang together. And the result is we get on the other side of all that is a nucleus of helium. That's what this is, and an extra neutron. So really what we get is fusion, and then we get decay, neutron decay, for the whole process to work. Let's see. Now a neutron, let's talk about these numbers right here. What do these numbers represent? Right here and here. The atomic number's here. The atomic mass is here. What is the atomic number? What? Number of protons. Okay. So if I have a neutron, I didn't mark the atomic symbology here showing mass and number of protons. How many protons in a neutron? It's a trick question. How many protons in a neutron? None. There's no protons in a neutron, so there's no atomic number in a neutron. The mass number we have at the top is the sum of protons and neutrons. So what's the sum of protons and neutrons in a neutron? Not a trick question. What's the sum of protons and neutrons in a neutron? What? Whatever. How many is it? How many neutrons in a neutron? If you keep guessing, you'll guess you'll get it, but yeah, it is one. You're right. Okay. The sum. This is the mass. This is the mass number at the top. The mass number is the sum of all the neutrons and protons. And so if we just have a neutron, then you have a mass of 1, right? So I could put 1 and 0 down here on this too. So in your list of references, this is where you say, oh, I can get that out. There's this chart called the Uranium Disintegration Series. Yes. The Uranium Disintegration Series. Notice at the bottom it says an alpha particle down here, but it shows what helium is, okay? I'd rather you use this version, so if you want to mark yours like I've marked mine, an alpha particle, I'd rather you not show that as being helium with a mass of 4 and atomic number of 2, but an alpha particle with a mass of 4, atomic number of 2. Okay? It is the same nucleus of a helium atom. An alpha particle is like a nucleus of a helium atom, but a helium atom actually also has 2 electrons. So I don't want to leave that way. I want to make sure we're kind of clear on what all that means. Okay? Well, this can be used to represent an alpha particle, but to me at least, I need to put a 2+ charge on here because if it's an alpha particle, it has no electrons. So I don't like that symbol, that's what I'm saying. Okay? Because this doesn't completely represent an alpha particle. If I put a 2+ charge in a superscript position here, yeah, then it's an alpha particle. But since it's not showing it here, I'd rather use this alpha particle symbol here with 4 and 2. Okay? All right. So what this is showing is the uranium decay series. So uranium, we had some uranium in our cloud chambers. And what did it give off? How did we get those vapor trails in that cloud chamber? No, it wasn't the dry ice that was causing it. The dry ice was making it cold, which gave us tiny droplets of ethanol, which allowed us to see what was happening. What? Well, the light helped us to see the vapor trail. What was that actually making the vapor trail? Huh? Well, the uranium ore was doing something. Why did we do this lab? It's giving away decay particles. Which decay particles were we looking at, or the results of which we were looking at? It was an alpha particle we were looking at. That's what was causing the vapor trails. Okay, that's okay. At least you're trying. Okay? It's the alpha particles that were causing the vapor trails. All right? They're the decay products. Alpha particles and beta particles, and for that matter, gamma radiation, are products of the decay of a nucleus. They come out of the nucleus. Okay? So, in that cloud chamber, the straight line cloud or vapor trails you saw were the result of alpha particles. If you saw some squiggly looking trails, they were beta particles. Yeah. Okay?